Welcome back to Talk Tensors. We love breaking down the absolute latest in machine learning research.
The best stuff.
And today,
Absolutely.
we're diving into a paper
Okay.
that tackles, this challenge that's super important in healthcare.
Yeah.
How do you keep machine learning models up to date when the data is just always changing?
Yeah.
Think about ECG data.
Yeah.
Like how that's used to detect arrhythmias in the heart.
Right.
There's always new data coming in from new patients.
Right.
New devices.
Of course.
Even the time of day can change the readings. It's just always in flux.
You've hit the nail on the head. This is where continual learning comes in.
Oh, okay.
And it's a very hot topic in ML right now. The goal is to create models that can just learn continuously from new data without forgetting what they've already learned.
Oh, okay.
Which is exactly what this paper explores.
Gotcha. So the paper we're looking at today is titled Dynamic Prototype Rehearsal for Continual Learning in ECG Arrhythmia Detection by Ramani and team.
Yeah.
I'm kind of curious, before we get into the specifics, why is this a big deal? Especially in the context of ECG arrhythmia detection.
So imagine you have a model, right?
Yeah.
And it's been trained to recognize different types of heartbeats.
Okay.
It's doing great. It's going along, doing a fantastic job. And then it encounters data that's a little bit different than what it's seen before. Suddenly it starts making mistakes.
Whoa.
This forgetting of previous information, this is called catastrophic forgetting.
Oh, wow.
And it's a major problem in medicine where accuracy is super important.
Right. So this isn't just about making models smarter. It's about making them safer and more reliable.
Yeah.
For real medical applications.
Exactly. And that's where the DreamCL method proposed in this paper comes in. It's designed to help models learn from this constant stream of new ECG data without falling victim to catastrophic forgetting.
Okay. So let's unpack how DreamCL actually works.
Sure.
The paper describes a 4-step process. I'm just curious to hear how it comes together.
It's a really clever approach.
Wow.
The first step is loss tracking, which is essentially figuring out where the model is struggling. So imagine you're a student, you're studying for an exam.
Okay. Yeah.
You want to focus on the problems that you keep getting wrong.
Right.
DreamCL does something similar. It tracks the model's errors or the loss to identify which data points it's having trouble with.
So it's not just about throwing more data at the model.
No.
It's figuring out what's the data that's most important to learn and to get better.
Precisely. And the next step, clustering, builds on that. Now that we know which data points are causing the model trouble, we group them together based on similarities in their errors.
Oh, okay.
It's like organizing your tricky exam questions by topic.
Oh, so instead of just seeing a jumble of hard problems,
right,
we're starting to see patterns emerge.
Exactly. Now comes the really interesting part. Smooth sorting and prototype selection.
Yep.
So within each cluster of those hard problems, DreamCL figures out, which are really tough, the ones that consistently trip up the model.
Yeah.
But here's the catch. It also accounts for potential outliers.
So it's not just about picking the hard problems, it's picking the right hard problems.
Exactly.
What do you mean by accounting for outliers?
So imagine in your study group, you have one person that usually aces everything, but occasionally makes some weird mistakes.
Oh, yeah.
DreamCL is designed to recognize those outliers and not be overly influenced by them when selecting the most important example.
Gotcha. That makes sense. So we've identified these super challenging examples. What happens next?
The final step is rehearsal.
Okay.
This is where the model reviews those tough problems alongside the new data. It's like going back and revisiting those tricky exam questions even as you continue to learn new material.
So it's like a targeted review session.
Exactly.
To reinforce the lessons and prevent that catastrophic forgetting.
Exactly. And what's fascinating is that the paper shows DreamCL actually outperforms existing methods when it comes to accurately classifying heart arrhythmias from ECG data, even as the data keeps changing.
That's impressive.
Yeah.
It sounds like it's a promising approach to tackle a really important problem in healthcare.
Yeah.
I'm curious, though, what are some of the specific challenges that researchers face when they apply continual learning to ECG data?
Well, one of the biggest challenges is just the sheer variability of ECG data. ECGs can look very different depending on the recording device, even the placement of the electrodes.
Oh, wow.
This makes it really hard for models to generalize what they've learned to new data.
So even if a model's learned to identify, certain arrhythmia in one set of ECGs,
Right.
it might struggle when it's faced with ECGs that look totally different,
Exactly.
even if they represent the same condition.
Exactly. And this is especially problematic for continual learning because as the model encounters more and more data, the risk of catastrophic forgetting just increases.
Yeah, that makes sense. It's like trying to learn a new language by listening to different dialects.
Right.
You might pick up the basics, but as you encounter more variations,
Right.
it becomes harder to retain it all.
That's a great analogy. And another challenge specific to ECG data is the temporal nature of the signal. An ECG isn't just a snapshot, it's a continuous recording of the heart's electrical activity over time.
So the model needs to be able to not only recognize individual patterns, but also understand how they change over time.
Precisely. And this adds another layer of complexity to continual learning, because the model needs to remember not only what it's seen, but also when it saw it.
That makes me think about how our own memories work. We don't just remember facts in isolation, but we remember them in the context of our experiences.
You're right, and that's a key insight that researchers are trying to incorporate into continual learning models. Now, to really appreciate the novelty of DreamCL, it's helpful to understand how continual learning has evolved over time.
Okay, so take us back to the early days. What were the initial approaches to tackling this problem of catastrophic forgetting?
One of the earliest and most intuitive approaches was to simply store a small subset of the old data and replay it to the model periodically alongside the new data. This is called rehearsal memory, and it's a simple yet effective technique.
So it's kind of like revisiting your old textbooks or notes when you're studying a new subject. You're reminding yourself of the fundamentals so you don't forget them as you learn new information.
Exactly. But as you can imagine, this approach has limitations. Storing and managing large amounts of data can get expensive and computationally intensive, especially as the model encounters more and more data over time.
So researchers needed to come up with more efficient ways to prevent forgetting without relying on massive data storage.
Exactly. And that led to the development of regularization-based techniques. These methods focus on modifying the learning process itself to make the model less prone to forgetting. One popular technique is called elastic weight consolidation, or EWC for short.
What's the basic idea behind EWC?
Imagine the model's knowledge is represented by a network of connections, kind of like pathways in the brain. As the model learns new information, those connections are strengthened or weakened.
So you're saying learning is like physically changing the structure of the model.
Precisely. And what EWC does is identify the connections that are most important for representing the old knowledge, and then make those connections stiffer or less likely to change when the model is learning new information.
So it's like protecting those core pathways from being overwritten by new experiences. It reminds me of how some memories are just more deeply ingrained than others.
That's a great way to think about it. And alongside regularization techniques, we also saw the emergence of meta-learning approaches. Here, the goal isn't just to make the model learn a specific task, but to make it learn how to learn.
So instead of teaching the model what to think, you're teaching it how to think.
Exactly. The idea is to train the model on a variety of tasks so that it develops a more general and adaptable learning strategy that can be applied to new tasks with minimal forgetting.
So by exposing the model to diverse experiences, it becomes more adaptable and less reliant on memorizing specific examples.
Precisely. And all of these different approaches to continual learning have their own strengths and weaknesses. DreamCL is particularly interesting because it combines elements of rehearsal memory with this sophisticated prototype selection and outlier handling we discussed earlier.
So it's kind of like taking the best of both worlds, combining the simplicity of rehearsal with the efficiency and robustness of more advanced techniques.
Right. And the results in the paper suggest that this combined approach is very effective, at least in the context of ECG arrhythmia detection.
That's exciting to hear. It sounds like DreamCL has the potential to significantly improve the reliability and safety of AI-powered systems in healthcare. But I'm also curious about the paper's analysis of how DreamCL handles data from different ECG leads. Can you explain what that's all about?
Sure. You see, a standard ECG actually records electrical signals from 12 different leads, each providing a unique view of the heart's activity.
So it's like looking at the heart from 12 different angles, each revealing the different aspects of its structure and function.
Exactly. And one of the interesting findings in the paper is that learning from data from different ECG leads seems to be particularly challenging for continual learning models.
It makes sense if you think about it. It's like trying to learn about a complex object by looking at it from different perspectives. You might think you understand it from one angle, but then you see it from another angle, and suddenly you realize there's more to learn.
Precisely. And this highlights a key area for future research in continual learning. How can we develop models that can effectively integrate information from multiple sources or perspectives without forgetting what they've already learned?
That's a fascinating question.
Yeah.
And it leads us perfectly into our novel notion segment, where we like to speculate on potential future directions for this research.
Oh.
But before we get too carried away with brainstorming, I'm curious to hear your thoughts on the limitations of DreamCL as outlined in the paper. Are there any potential drawbacks or areas where further research is needed?
Yeah, that's a great question. And it's always important to, consider the limitations of any new research.
For sure.
What did the authors point out as potential areas for improvement?
Well, one thing they highlighted is that DreamCL's performance, like many machine learning techniques, can be sensitive to something called hyperparameters.
Okay,
These are like settings that control how the algorithm works.
gotcha.
In DreamCL, one of these hyperparameters is the size of the rehearsal memory. So you're saying that finding that sweet spot for how much old data to store
Yeah.
is really important.
If the rehearsal memory is too small, the model might not have enough examples to prevent forgetting.
Right.
But if it's too large, it can become really computationally expensive to manage.
Makes sense.
Finding the right balance is key.
It's a classic trade-off between remembering everything and keeping things manageable.
Right.
Were there any other limitations that they discussed?
Another point they raised is that DreamCL, at least in its current form, relies on supervised learning.
Okay.
This means it needs data that's already been labeled with the correct answers.
Right.
Like which ECG patterns correspond to which arrhythmias.
This is like a student that needs a teacher to point out the right answers as they learn.
Exactly.
But in the real world, labeled data can be scarce or expensive to obtain,
Absolutely.
especially in medicine.
Especially in medicine.
So a promising direction for future research is to explore how to adapt DreamCL to unsupervised or semi-supervised setting, where the model has to learn with less guidance.
Precisely.
I can't resist diving into our novel notions segment now,
Okay.
where we let our imaginations run wild a little bit.
I like it.
If we could build on the ideas in this paper, what are some exciting new directions you see emerging in continual learning?
Oh, there's so many possibilities.
Yeah.
One area I find particularly intriguing is the idea of moving beyond simply remembering hard problems to anticipating them.
Wow.
What if we could develop systems that could proactively identify potential challenges or biases in the data and adjust their learning strategies accordingly?
It's fascinating.
Yeah.
So you're saying take continual learning to the next level, from reactive to proactive.
Exactly.
Instead of waiting for the model to make mistakes, we're trying to anticipate those mistakes
Right.
and prevent them from happening.
Precisely. And this would require developing new algorithms that can not only learn from data, but also learn about the data itself.
Oh, wow.
Understanding its limitations, its biases, and its potential pitfalls.
So it's almost like we're asking the model to become a data scientist itself,
That's a great analogy.
constantly evaluating the quality and reliability of the information it's receiving.
Yeah. And another direction I see emerging is this integration of continual learning with other areas of machine learning,
Okay.
such as reinforcement learning.
Uh-huh.
Imagine systems that can learn from their interactions with the environment, continuously adapting and improving their behavior over time.
That makes me think about robotics or autonomous systems,
Exactly.
where that ability to learn on the fly is crucial.
Exactly. And in healthcare, this could lead to the development of personalized treatment plans that adapt to a patient's changing needs and responses.
That's really cool.
Yeah.
It's incredible to think about all the possibilities.
It is.
But as with any emerging field, there will always be challenges.
Absolutely.
Hmm.
But this research on DreamCL is a significant step forward,
Yeah.
demonstrating the potential of continual learning to address real-world problems, particularly in healthcare.
Well, on that note of optimism and future possibilities, we've reached the end of our deep dive into this remarkable paper on continual learning in ECG arrhythmia detection.
It is a cool paper.
As always, we encourage you to check out the full paper. It's linked in our show notes.
Please do.
And be sure to join us next time for another fascinating exploration of cutting-edge research in the world of machine learning.
I can't wait.
Until then, keep those neural networks firing
Yes!
and those intellectual gears turning.
Keep thinking.
From all of us here at Talk Tensors, thanks for listening.
Thank you.